Hello guys, welcome to our channel Naiperian Solutions. So today we are going to discuss about the organic chemistry, right? So that is also very important subject from your FDA chemical analyst exam point of view. So that lecture is very important, right? So we will discuss one by one what are the things that we will cover in this lecture. So SN1 and SN2 reactions, differentiative test for alcohols, differentiative test for amines, name reactions, very important, right? So that specifically this section name reactions is very important from your exam point of view. Then acidity of phenols, acidity of aromatic acids, and basicity of amines, right? So these are the points that we are cover in this our session, right? Okay, so the start with our SN1 and SN2 reactions, right? So here is an important table that is differentiate between the SN1 and SN2 reactions, because the most of the times in like nucleophilic substitution reactions they are just asking like the differentiating points of the SN1 and the SN2 reaction, right? So we will see one by one what are the points. So first one is the rate law. In SN1 reaction, that is the unimolecular. Similarly in SN2, that is the bimolecular. So what is unimolecular? Means that rate of reaction is depend only on your substrate, right? And in SN2 reaction, that is the substrate as well as your nucleophile. Big barrier. So what is the big barrier in SN1 reaction? That is the carbocation stability, right? So that is the main important factor in your SN1 reaction. And what about SN2 reaction? This is the steric hindrance. Similarly in alkyl halide or whatever the electrophile that you are using in your reaction, so the tertiary is means fastest, then secondary, and then primary. But in SN2 that is totally opposite. So primary, then secondary, and then tertiary, right? So that is very important, guys. Then nucleophile, right? So we have seen the electrophile, now nucleophile. So what kind of nucleophiles that are the weak in SN1 reactions, but in SN2 reactions the nucleophile are very strong, right? Because they are bearing a like negative charge. So solvents like polar protic solvents using in the SN1 reaction, but in SN2 reactions the polar aprotic solvents. So examples also given, so please remember this one. Then stereochemistry, right? So that is also very important. So most of the times they have asked, so mix of retention and inversion in the SN1, but in SN2 there is a strictly inversion, right? Inversion chemistry in the SN2 reaction. So here are some points. So steps in SN1 reaction, that SN1 reaction is a two-step reaction, right? But SN2 reaction is a single step because there is a transition state. And the reaction kinetics, the SN1 follows the first order kinetics, whereas SN2 reaction follows the second order kinetics. So what is the first order kinetics? Means rate of reaction depends only on the haloalkanes, not on the nucleophile, right? That already we have seen. And in SN2 reactions it is dependent on the both substrate as well as your nucleophile. I hope that differentiating points of the SN1 and SN2 is clear to you, right? So please guys remember this one because this is very important. Okay, the next one, sorry. Okay, the next one, the differentiating test for the alcohol, right? So this is also very important, that is the Lucas test. What is the test? Nothing but the your Lucas test. So what is the Lucas reagent? So that is nothing but the zinc chloride plus hydrochloric acid. And what is the reaction type? That is the nucleophilic substitution reaction. So similarly here are the differentiating alcohols like primary alcohol, secondary alcohol, and tertiary alcohol. So how we will differentiate in between these alcohols, right? So primary alcohol, when react with the zinc chloride and HCl, there is a no reaction, right? Very important. In primary alcohol there is a no reaction, right? But in secondary and tertiary alcohol, then how will you differentiate between secondary and tertiary? So in secondary alcohol reaction takes place in 3 to 5 minutes, right? Here reaction takes place in 3 to 5 minutes. And in tertiary alcohol reaction is very immediate, instant reaction is there in the tertiary alcohols. So accordingly you will differentiate your alcohols depending on your Lucas reagent, right? So this test is also very important. Please remember which reagent is this. That is the zinc chloride plus HCl. Okay. Okay. The next one, the differentiative test for amines. That is the Hinsberg test. So what is the reagent in the Hinsberg reagent or in the Hinsberg test? That is the benzene sulfonyl chloride and KOH, potassium hydroxide. So again here we have to differentiate in between primary amines, secondary amines and tertiary amines. So in primary amine, again react with your benzene sulfonyl chloride and KOH, and what is the product? That is the N-alkyl benzene sulfonamide. So which is soluble in alkali. Then secondary amines, that the product is the N dialkyl benzene sulfonamide and which is insoluble in alkali. And tertiary amines, there is a no reaction of tertiary amines. Please remember this guys, in between alcohols and amines. In alcohols, primary alcohols, there is a no reaction, and in amines there is a no reaction in the tertiary amines. Okay, here is the reaction. So this one, right, so this one is your benzene sulfonyl chloride react with your primary amine. Okay, so your product is like alkyl benzene sulfonamide. Okay, alkyl benzene sulfonamide, just N alkyl, because here is only one R is there. Okay, so that is about the primary one, and which is soluble in alkali. Just previously we have seen your primary amine, which is whatever the product that is formed by the reacting with the benzene sulfonium chloride and KOH, that is the soluble in alkali. So similarly in secondary amines, right, so what is the product? That is N dialkyl benzene sulfonamide. Okay, here is the product. What it is? N dialkyl benzene sulfonamide, which is insoluble in alkali, right? And the tertiary, right, here we have seen the tertiary amines, there is no reaction of tertiary amines, right? So these are the differentiating points of the amines, right? Primary amines, the product is our alkyl benzene sulfonamide. Then in secondary amines, there is N dialkyl benzene sulfonamide, and in tertiary amines there is a no reaction. Please remember these points, very very important. So these two tests are very important: Lucas test for the alcohols and the Hinsberg test for the amines. What is the Lucas reagent? That is the zinc chloride plus HCl. And what is the Hinsberg reagent? That is the benzene sulfonium chloride. Okay. Okay. So now we are moving towards the name reactions. So first one is the Woods reaction. So what is the Woods reaction? Then alkyl halides react with a sodium in a dry ether to give hydrocarbon containing double the number of carbon. That sentence is very very important. Double the number of carbon atom present in the halide. Whatever the halide you are using and whatever the product, right? So the product always containing the double number of carbon. Okay. Here you can see, here is 2RX, right? Alkyl halide you are using, but in the product 2R is there, right? Means the number of carbons whatever that you are using, that is the double the number of carbon in the product. Okay, what is the Woods fatigue reaction? So similarly here is the aromatic chloride or chlorobenzene, right? Similarly we are calling as a chlorobenzene, a mixture of an alkyl halide and aryl halide. Okay, means here are the mixture of aromatic and aliphatic, right? Gives an alkyl arenes, right? What it is giving? Alkyl arenes, right, when treated with a sodium in dry ether, right? And what is the this reaction? Fatigue reaction. Similarly Woods reaction and fatigue reaction is that completely similar. Just here in the Woods reaction they are using a like alkyl means non-aromatic, instead of non-aromatic I am saying like aliphatic compounds, right? And similarly in the fatigue reaction, this is for the our aromatic compounds. So in fatigue reaction, two R groups or the two benzene groups here, right? Okay, here the two benzene groups that has formed bond, which is the diphenyl compound. So please differentiate in between these reactions also: Woods reaction, Woods fatigue reaction and fatigue reaction, right? Similarly just these are the like which one is aromatic, which one is aliphatic, which one is the combine of the aromatic as well as aliphatic. So the Woods fatigue reaction, this one is the combination of the aromatic and aliphatic. Okay. So the next one, okay, Clemenson's reduction and the Wolff-Kishner reduction. Okay. So in Clemenson's reduction, the compound in the both reactions are the same. Okay. So just see one by one. What is the Clemenson reduction? The carbonyl group of aldehyde or ketone is reduced to your CH2 group. Okay, that's clear. On a treatment with zinc amalgam and concentrated HCl, right? Similarly, in Wolff-Kishner reduction, the carbonyl group of your aldehyde or ketone, that is converted into the CH2 group or reduced into the CH2 group. Just the reagent is different. Here is the hydrazine, right? In Wolff-Kishner reduction, your reagent is the hydrazine we are using, but your compound is similar, right? So just this is the differentiate in between these two reagents. In Clemenson reduction, we are using the zinc amalgam and concentrated HCl, and while in Wolff-Kishner reduction, we are using the hydrazine as a reagent. Okay. Okay, the next Williamson reaction, that is very well known reaction, we all know. Williamson, also called as the Williamson ether synthesis, right? Similarly, like ethyl iodide react with the sodium ethoxide and it is forming diethyl ether, or here in aromatic compound sodium phenoxide react with methyl iodide, it is giving our anisole, right? Okay, Stephen reaction, that is very important. Stephen reaction, just simply conversion of your cyanide into your aldehyde, right? CN bond converted into your aldehyde by using the tin chloride and hydrochloric acid followed by your hydrolysis. Okay. In this reaction, one important point that you have to remember is acetaldehyde hydrochloride. That is the intermediate form in this reaction, right? What it is? Right? Acetaldehyde hydrochloride. Okay, just that is the point is important. And reaction is also very important. Cyanide converted into your aldehyde. Okay. Okay, the next reaction, Schmidt reaction, right? So again here, that Schmidt reaction involves the your benzoic acid or any carboxylic acid that undergoes the reaction with, okay, here that N3H is there, okay, N3H. So don't get confused between NH3, that is not the ammonia, okay, that is the N3H, that is the hydrozoic acid and the concentrated H2SO4, okay. So benzoic acid react with your hydrozoic acid and concentrated H2SO4, you will give the aniline as a product. So similarly, you can see here, right, in this one, your carboxylic acid react with your hydrozoic acid and concentrated H2SO4, you are giving the primary amines, means carboxylic acid gives the primary amines, but in here in the second reaction, the ketone does not give your primary amines, right? So ketone gives similar reagent we are using, but ketone gives the amides. Okay, ketone gives amides. Similarly, aldehydes, okay, we have seen carboxylic acid, we have seen ketones, but what about aldehydes? So aldehydes are also giving the primary amines, right? Please remember, aldehyde are also giving the primary amines. Just ketone is giving the amides. Okay. So the next reaction, that is Schotten-Baumann reaction, right? So what is the Schotten-Baumann reaction? Right? It is the reaction between your primary amine or your acid chloride to give your amide compounds. Okay. So similarly, instead of your amine, if you are using the phenol, right? So similarly, here is the amide form, right? So that is the Schotten-Baumann reaction. But instead of your amine, right, instead of this one, you are using your phenol. So phenol react with your benzyl chloride, right? That is nothing but your acid chloride. Okay. So phenol react with your acid chloride in the presence of that base. So it is giving the phenyl benzoate, right? So that is the Schotten-Baumann reaction. That is also very important. So next one, Sandmeyer reaction. The chlorine, bromine and cyanide nucleophile can easily be introduced in the benzene ring of benzene diazonium salt in the presence of copper 1 ion. Okay. So simply what we can say, so that is the diazonium salt reactions. Okay, right? What is the Sandmeyer reaction? That is the diazonium salt reactions, that is the benzene diazonium chloride. Okay, so how you are forming the benzene diazonium chloride, right? So that is the diazotization reaction. So from the diazotization reaction you have to synthesize your benzene diazonium chloride, and that benzene diazonium chloride react with the copper 1 ion. That is very important. Copper, what is the oxidation state of copper in the Sandmeyer reaction? That is the 1, right? Copper 1 reaction, that is not a copper iodide, right? Please remember, this is the copper ion only, and the 1 is the oxidation state of your copper, right? Copper 1. So similarly, like benzene diazonium chloride in the presence of CuCl, right? So you will get chlorobenzene. Similarly, in the CuBr you are getting bromobenzene, and CuCN you are getting the your benzonitrile or cyanobenzene, right? So Sandmeyer reaction, that is basically example from your diazotization reaction. Whatever the diazotization reaction that takes place, and then that benzene diazonium chloride reacts with your copper compound, so then you will get your chlorobenzene or your halobenzene. That is the Sandmeyer reaction. Similarly, one more reaction of the, like similarly here Gattermann reaction, right? So simply the product is very similar, like Gattermann reaction and the Sandmeyer reaction product is very similar, because here is also benzene diazonium chloride you are using. Okay, so that benzene diazonium chloride, chlorine or bromine can be introduced in the benzene ring by treating the benzene diazonium salt solution with corresponding halogen acid in the presence of copper powder, right? In the Sandmeyer reaction we are using the copper compound, that is the oxidation state is 1, but here we are using the copper powder, right? CuHCl or CuHBr. So here HCl or HBr, that is very important, because if you are using the HCl then you will get the chlorobenzene, or if you are using the HBr then you will get the bromobenzene. But in Sandmeyer reaction, like CuCl, CuBr or CuCN, right, that you are using. So that is the basic difference in between the Sandmeyer reaction and Gattermann reaction. So Gattermann-Koch reaction, so that is also like synthesis or if aldehyde benzene, right? So whatever the benzene molecule or the substituted benzene that you are using, so for that one benzene is react with like your carbon monoxide, right? Carbon monoxide and hydrochloric acid. So it is forming the formyl chloride, and the formyl chloride react with your benzene in the presence of your aluminum chloride or the copper chloride, then you will get the benzaldehyde, right? Means simple reaction, benzene react with carbon monoxide or the hydrochloric acid in the presence of AlCl3, you are getting your respective aldehyde. That is nothing but your Gattermann-Koch reaction. Next one, the Rosenmann reduction or the Rosenmann reaction, that is the simply reduction reaction or the Rosenmann reaction. Acyl chloride or the acid chloride is hydrogenated over catalyst. What is the catalyst? Very important in Rosenmann reduction. Most of the time they have asked what is the catalyst in the Rosenmann reduction. So what is this? That is the palladium on barium sulfate to form a aldehyde, right? In this reaction also we are forming the our aldehyde, and what is the acid chloride is react with PDBaSO4, right? Means the Rosenmann is the example of reduction reaction, here using the hydrogen, okay, hydrogen they are using, and what is the catalyst? That is the PDBaSO4, right? Palladium barium sulfate, and what is your product? That is your aldehyde. Whatever the aldehyde that you are using, that is your product. Okay, the next reaction, that is the Reimer-Tiemann reaction, right? On treating phenol with chloroform in the presence of sodium hydroxide, a CHO group is introduced at ortho position of benzene ring, resulting a salicylaldehyde. Simply reaction, that is the reaction simply says that is the phenol reacting with your chloroform in the presence of your alkali, that is forming your salicylic acid or 2-hydroxybenzoic acid. Very important guys, this is the ortho formulation of phenol. That reaction, Reimer-Tiemann reaction, is nothing but the ortho formulation of your phenol. Okay, so the next one, that is the Kolb-Schmidt reaction. Then again phenol is react with your carbon dioxide and NOH, and then you will form your phenoxide ion, and that phenoxide ion you are treating with your H2SO4, you will again get your 2-hydroxybenzoic acid, that is the salicylic acid, right? So phenol with sodium hydroxide gives the sodium phenoxide ion, which with carbon dioxide in acidic medium results hydrobenzoic acid or the salicylic acid. Means this compound, right, that is the phenol. So phenol is react with the firstly with base like NaOH, and it is forming the C6H5ONa, right, phenoxide ion, right? So that phenoxide ion again react with your CO2, so then only this compound will form, right? And then you are treating with your H2SO4, then you will get the 2-hydroxybenzoic acid or the salicylic acid. Means there are the two reactions which are forming the salicylic acid. One is the Kolb-Schmidt reaction, right? And then another one is your Reimer-Tiemann reaction, right? So please remember these two reactions which are forming the, so what is the product in these two reactions? That is the your salicylic acid. Okay, very well known reaction, Hofmann bromamide reaction. Okay, an amide with bromine in an aqueous or ethanolic solution of sodium hydroxide gives primary amines, right? Means Hofmann reaction basically for your primary amines, right? In this degradation reaction, migration of an alkyl or aryl group takes place from carbonyl carbon of the amide to the nitrogen atom, right? The amine formed contain one carbon less than that of present in the amide, right? So guys, simply this is the reaction which involve your amide, right? Primary amide to primary amine, right? And what is the statement? Means one carbon less from your amide, right? In compound there is one carbon less. You can see here that there is a primary amide R C double bond O NH2, but in your product you can see that is the R NH2. Means C double bond O, that is reduced or that is removed from here by using the different reagents, right? And what are the reagents? Reagents is also very important in this reaction. That is the Cl2 or Br2, then using the base like NaOH, right? Water, hydrolysis, and very important thing in this reaction, what is the intermediate? That is the isocyanate, right? Because when your primary amine formed after the hydrolysis of your isocyanate, right? So means amide converted into the amines. So what is the reaction? Hofmann bromamide reaction. That reaction is very important, guys. Okay, the next one, Hale-Hollard-Zielinski reaction, right? Carboxylic acids having an alpha hydrogen. That word is very important, right? Having an alpha hydrogen, right? Means ऐसा कार्बोक्सिलिक एसिड जिसमें कि अल्फा हाइड्रोजन प्रेजेंट होना चाहिए, then and then only Hale-Hollard-Zielinski reaction is possible. So similarly you can see the example here, that is the acetic acid, right? So here alpha hydrogen is present in your acetic acid because that first one is the alpha carbon, and whatever the hydrogen attached to that alpha carbon, these all are the your alpha hydrogens, right? So what is that reaction is saying? The carboxylic acid having an alpha hydrogen are halogenated at the alpha position on treatment with chlorine or bromine in the presence of small amount of red phosphorus, right? So what is the reagent here? That is the red phosphorus and chlorine or the bromine, and right, what is the alpha position is halogenated, right? Means whatever the carboxylic acid which is having the alpha hydrogen, that hydrogen is replaced with your halogen, that is nothing but your Hale-Hollard-Zielinski reaction, right? And what is your compound? That is alpha halo carboxylic acid. Means your carboxylic acid converted into your alpha halo carboxylic acid. Okay, here alpha halo carboxylic acid and your carboxylic acid with alpha hydrogen. So that is two terms are very important. Your carboxylic acid should have your alpha hydrogen, and what is your product? That alpha hydrogen is replaced with the halogen, and that is the alpha halo carboxylic acid formed in the Hale-Hollard-Zielinski reaction. I think this is very fast, but we have very less time because lecture is very lengthy and we have to cover all the important reactions, right? Okay, the Reformatsky reaction. The Reformatsky reaction is the reaction of a carbonyl compound, usually an aldehyde or ketone, with an alpha halo ester in the presence of zinc to give beta hydroxy ester, right? So this statement is very important. You have to remember the alpha halo ester, that is your starting material, right? So alpha halo ester reacts with your aldehyde or ketone, right? So alpha halo ester plus aldehyde or ketone, what is the product you are getting? That is the beta hydroxy ester. So in reaction you can see this one, that is your alpha halo ester, right? So what is the alpha? That is the alpha halo, okay, in that X here. So that is the alpha halo ester, here is ester, and at alpha position there is X. X should be your chlorine, bromine, iodine, whatever, right? So that is the alpha halo ester react with your aldehyde or ketone, or simply we can say our aldehyde or ketone react with the alpha halo ester in the presence of zinc, okay. And what is the product? Product is our beta hydroxy ester, right? So here in the alpha position R2 is there, and in the beta position hydroxy group is there, means beta hydroxy ester, means your aldehyde or ketone react with your alpha halo ester in the presence of zinc, then you will get your beta hydroxy ester. So starting material, whatever the reagents you are using, and what is the product, and what is the specificity of that name reaction, these are the important points in the name reaction. Specifically the product and the intermediates or the catalyst that you are using. Okay, the next one, Gabriel thalamide synthesis, right? So this is also very important reaction. Similarly, this reaction we are using in the synthesis of our amino acids, right? So in the synthesis of amino acids also we are using the Gabriel thalamide synthesis or the synthesis of your primary amines. So in Gabriel synthesis is used for the preparation of pure primary amines. Thalamide on treatment with alcoholic KOH form potassium salt of thalamide, which on heating with alkyl halide followed by alkaline hydrolysis produces the corresponding primary amine, right? So what it says simply, your thalamide is react with your alcoholic KOH, right? And then again it is converted into the potassium thalamide, right? And there are the intermediate, this one, this is your intermediate, right? And ethyl thalamide, and that is on hydrolysis you will get your phthalic acid and ethyl amine, right? Phthalic acid, this one, and this is your ethyl amine, right? So how this product is formed? Because the hydrolysis is there, okay, hydrolysis, but at what position? That hydrolysis is here, okay, means the two H2O molecule are present over there. So due to that hydrolysis, that molecule is converted into the phthalic acid plus your ethyl amine. Okay, the last one, very important one. So that aromatic primary amines cannot be prepared by this method, right? Means which kind of amines is not prepared by this method? That are the aromatic primary amines, okay. Because why? Because aryl halides do not undergo nucleophilic substitution with the anion formed by your thalamide. So that's why this is the reason aromatic primary amines are not formed by Gabriel thalamide synthesis reaction. I hope this reaction is clear. Okay, the next one, that is the halogen exchange reaction. So there are two reactions, right? Halogen exchange reactions. So these are two reactions of halogen exchange. First one is your Wilkinson reaction and the Schwartz reactions. So if you are looking to the reaction, so you also simply understand why these are the halogen exchange reactions. So in Wilkinson reaction, alkyl iodide are prepared by the reaction of alkyl chloride or bromide with sodium iodide in dry acetone. That is important. What is the reagent? Sodium iodide in your dry acetone. That is nothing but your Wilkinson reaction. Similarly, in the Schwartz reaction, that is the heating an alkyl chloride or bromide in the presence of metallic fluoride. Here are the reagents are different, right? Metallic fluoride such as silver fluoride, Hg2F2, mercurous fluoride, that is COF2 or SbF3. So these are also giving the simple alkyl fluorides. Means just in these both reactions your halogen is substituted, right? Or your halogen is exchanging in these both reactions. So you just in these two reactions you have to remember what kind of reagents in which reactions, right? So sodium iodide in dry acetone that you are using in the Wilkinson reaction, and your metallic fluoride such as silver fluoride and all this one, these are using in your Schwartz reaction. Next one, Itard reaction, right? So in that Itard reaction, chromyl chloride, right? So your toluene react with your chromyl chloride, that oxidizes the methyl group to a chromium complex. Here you can see your chromium complex, okay, which on hydrolysis gives the corresponding benzaldehyde. Means if you are reacting with toluene, then you are getting benzaldehyde as a product, and reagent is very important in this reaction, that is your chromyl chloride. That is your Itard reaction. Means again this reaction is forming the benzaldehyde, okay. So the next reaction, Claison's condensation. The Claison condensation is a CC bond forming reaction, means carbon carbon bond forming reactions, that occurs between two esters or one ester and one carbonyl compound in the presence of strong base, right? So strong base is the requirement, right? What is the requirement? That is the strong base. Means two esters or one ester and one another is a carbonyl compound. So that is the basic requirement of the Claison condensation. The reaction produces a beta keto ester or a beta diketone, okay. So you have to remember what is the product of the Claison condensation, that is the beta keto ester or a beta diketone, right? So two esters are reacting. Here you can see this one and this one. So here are the two esters in the presence of strong base NaOR, right? That is the like sodium alkoxide, right? So this is very very strong base, sodium alkoxide, further followed by the hydrolysis, and you will get the beta keto ester, okay, beta keto ester. Alcohol is your secondary product, right? So, but you have to remember the beta keto ester. Which reaction is forming the beta keto ester? That is the Claison's condensation. Here is the simple example. Two molecules of ethyl acetate, right, reacts with the sodium ethoxide, that is very strong base, followed by the hydrolysis. You are getting the ethyl acetoacetate, right? What you are getting, that ethyl acetoacetate, means that is the beta keto ester or the beta diketone. So how it is the beta keto ester, right? Similarly here you can see, right, in the beta keto ester this structure, right? In the beta position, right, there is a ketone group, right? Here is a alpha and this one is the beta, so beta keto, okay. So in from both the sides you are getting the beta keto ester or the beta diketone. So that is very important, okay. The Cannizzaro reaction, that is also very important reaction from your aldehyde topics or your carbonyl compounds. So here is aldehyde which do not have an alpha hydrogen atom. Again that is very important, right? What kind of aldehyde you are using which do not have a alpha hydrogen atom? So what are the examples which do not have the alpha hydrogen atom? So simply first one is the formaldehyde and another one is the benzaldehyde. So these are very well known like compound which do not have a alpha hydrogen atom. Here you can see in formaldehyde hydrogen is there, but that is not the alpha hydrogen because there is no alpha carbon in the formaldehyde. And in similarly in benzaldehyde also, that aldehyde is directly attached to that carbon, but there is no hydrogen in that benzene ring. There is a no hydrogen present from that first like carbon, right? That carbon carbon bond. Means benzaldehyde and formaldehyde, these are the two aldehydes which do not contain the alpha hydrogen atom. That's why these are going under the Cannizzaro reaction, okay. So what is the simple reaction? Aldehydes which do not have an alpha hydrogen atoms undergo the self oxidation and reduction on the treatment with concentrated alkali, right? So what is concentrated alkali? That is the NaOH 50%. So in this reaction one molecule of the aldehyde is reduced to alcohol while another is oxidized to the carboxylic acid salt. So similarly you can see in the formaldehyde you are getting the product methyl alcohol and sodium formate, and in benzaldehyde you are getting the benzyl alcohol and the sodium benzoate. So that is the example of Cannizzaro reaction. Very important point that you have to remember, that do not have an alpha hydrogen atom in your aldehyde. That is the basic point of Cannizzaro reaction. Okay, the next one, that is the Ball-Simon reaction. When arene diazonium chloride treated with fluoroboric acid, then arene diazonium fluoroborate is precipitated, which on being decomposes to yield an aryl fluoride. Okay, what that reaction simply says means that aniline, then Na2HBF4, and what is the temperature? That is the 273 to 278 Kelvin. Means here is the intermediate is forming the benzene diazonium tetrafluoroborate. But in this between there is one step is there, that is your diazotization reaction, right? Means your aniline is converted your that diazonium salt, and the diazonium salt, if you are reacting with HBF4, what is HBF4? That is the fluoroboric acid. You are getting this intermediate, and if that intermediate again converted into the fluorobenzene. So you have to remember the compound fluorobenzene. Means again Bals-Kieman reaction is from your diazotization reaction type, right? But means that aniline is again converted into your like benzene, that benzene diazonium salt, right? And again that benzene diazonium salt is treating with your fluoroboric acid. You are getting the benzene diazonium tetrafluoroborate, and finally you are getting the fluorobenzene. So Bals-Kieman reaction is nothing about the fluorobenzene. What is your product? Fluorobenzene. Next reaction, Curtius reaction. The Curtius reaction is the thermal decomposition of an acyl azide to an isocyanate with loss of nitrogen gas. The isocyanate then undergoes the attack by a variety of nucleophiles such as water, alcohol and amines to yield a primary amine, carbamate and urea derivative respectively. Okay, so just see that diagram of this reaction. So acyl azide converted into your isocyanate, right, by the presence of heat, and the nitrogen molecule is removed in the first step. But how that acyl azide is formed, guys? That acyl azide is formed when your carboxylic acid treated with your sodium azide, right? Carboxylic acid RCOOH, right? So RCOOH, right? So converted into that acyl azide in the presence of sodium azide. Means carboxylic acid and sodium azide, that reaction that is forming the acyl azide. That acyl azide again on heating, that N2 is removed, means it is forming the isocyanate, and depending on your nucleophile, here are the three different one. Okay, right? So depending on your nucleophile, you are getting your product. So generally on water hydrolysis, you are getting your primary amine. So that is your Curtius reaction. Similarly, one more reaction we have seen, that is forming the isocyanate as an intermediate. What is the name of that reaction? That is our Hofmann bromamide reaction. So Hofmann bromamide reaction and the Curtius reaction, these are forming the isocyanate as a intermediate. Okay, then the coupling reactions. So again the coupling reactions of your benzene diazonium chloride, right? Means your benzene diazonium chloride react with phenol, and the benzene diazonium chloride react with your aniline. Here benzene diazonium chloride is there, here is your phenol, right? Similarly here is aniline, that is the difference only. So that is the coupling of between this benzene diazonium chloride and phenol. You are getting the para hydroxybenzene, that is the orange dye here, right? And similarly, if that benzene diazonium chloride is react with your aniline, you are getting your para amino benzene, right? That is the yellow dye. Okay, means orange dye and yellow dye, right? Because this is just a coupling reaction, right? Okay, so the next point. So here we have completed most of the important reactions which are very important in the organic chemistry. So please look into that, and all the reactions are very important for your exam point of view. So just you have to remember from your name reactions, what are the reagents that you are using, what are the products, which reactions are forming the aldehydes, which reactions are forming the salicylic acid, what are the reagents, right? If sometimes there is a differentiating point in between two reactions, right? So that small points from your name reactions that are very important. So the next one is the acidity of phenols, right? So generally our carboxylic acids are more acidic than your aromatic OH, means that is the phenol, and then aliphatic alcohols, right? So what is the order here? that is your carboxylic acid, then phenol, and then alcohol. Means phenol are more acidic than the alcohols but less acidic than your carboxylic acid. Okay, यहाँ तक सब क्लियर है. योर फिनॉल्स आर मोर एसिडिक देन अल्कोहल्स बट लेस एसिडिक देन योर कार्बोक्सिलिक एसिड. अभी हम देखते हैं कि ऐसा क्यों है. ठीक है, क्यों है? क्योंकि फिनॉल में फिनॉक्साइड आयन फॉर्म होता है. व्हाट इट इज फॉर्मिंग? दैट इज द फिनॉक्साइड आयन. ओके, सो ड्यू टू दैट फिनॉक्साइड आयन योर फिनॉल्स आर more acidic in nature. Why? Because comparatively phenoxide ions are more stable, right? Phenoxide ions are more stable than your alkoxide ion. Whatever the ions forming in your like aliphatic alcohols, the phenoxide ions having the more stability than your alkoxide, right? So here in the first point, due to the stable phenoxide ion, that's why the phenol are more acidic than your alcohol. In alkoxide, stability is less because no resonance, right? Why? Because in your alkoxide ion there is no resonance and there is no delocalization of your electrons. So that's why your phenols are more acidic. Then atom with more S character in their hybridization state are more stable when leaves H plus ion, hence more acidic in nature. So simply we know whatever the compound which releases the H plus ion, these are the acids, right? So whatever the compound, these are releases the H plus acid, these are the acids. Okay, so here is the effect of hybridization, right? Means if you have S character more, right, which is like more S characters, like suppose in sp hybridization. So here are the in sp hybridization character is 50-50%, right? So similarly in like sp3 and sp2 hybridization. Okay, in sp3 hybridization, here you can see guys, in here, okay, in sp3 hybridization that S character is 25%, okay, and in sp2 hybridization S character is 33.33%. okay, so here we are concluding that in phenoxide ion the S character is more, that is the 33.33% as compared to your alkoxide ion. okay, यहाँ तक सब क्लियर है. इन फिनॉक्साइड आयन योर S character is more, that is the 33.33%, and in alkoxide ion that is the 25% only. Why? Because in alkoxide ion, right, in alkoxide ion that is directly attached to your carbon. okay, so that is the sp3 carbon, but in phenoxide ion, right, in that phenoxide ion that is directly attached to your that carbon which is the sp2 hybridized, right? In the structure of your phenoxide ion there is a sp2 hybridized carbon. Similarly in alkoxide ion there is a sp3 hybridized carbon. So here we are concluding the S character is more in the phenoxide ion, so hence phenoxide ion becomes more stable and hence phenol are more acidic than alcohols, right? I hope this is very clear to you guys, the acidity of phenol. It is depending on your hybridization, it is depending on your phenoxide ion, right? So what is the ortho and para position, right? So what is the effect of similarly in electron withdrawing group and electron donating group or the electron releasing group, right? So that point is very important. Here you can see, so basically electron withdrawing group. So what is the effect of electron withdrawing group on acidity? So if any electron withdrawing group attached to your ortho or the para position, your acidity is increasing. Please remember, if any electron withdrawing group attached to ortho or the para position, your acidity of your phenols are increasing, while the electron donating group attached to the ortho or para position, your acidity of phenol is decreases. Means simply that is the effect of your electron withdrawing group and electron donating group, right? So means electron withdrawing groups are the electronegative, means minus I effect is there, right? And electron donating group there is a plus I effect is there, or these are the electron releasing group. Okay, so that point is very very important guys, acidity of phenols. So please go through it. Okay, Then acidity of aromatic acids. So similarly here also, right, in aromatic acids that COH group directly attached to sp2 carbons, while in R COOH means aliphatic carboxylic acids, COH group directly attached to the sp3 carbon, right? So that is very simple, right? That is very basic, this point. In this one, in first one, the carboxylic group directly attached to sp2 carbon means that is more electronegative comparatively as compared to the sp3 carbon. Whatever the COOH group is directly attached to the sp2 carbon, that is the more electronegative in nature. Okay, so what is the like order of acidity in aromatic one? So there is aromatic carboxylic acids are more acidic than your aliphatic like carboxylic acids. Okay, so simply we have seen in the phenols. So similarly that rule apply here only, right? Means if any molecule that is more electronegative or directly attached to the sp2 carbon, right, so these are the more acidic. Okay, so in ortho and para position, similarly here we are seeing the effect of electron withdrawing group on acidity. So acidity increases, and the electron donating group, so acidity decreases. So here in this diagram you can see so that all the effects, right? Okay, so in the first three one or the first two one, there is electron donating group methoxy and methyl is there, so acidity decreases, right? So what is the pK? 10.2 and 10.19. so means acidity decreases due to the effect of electron donating group. And similarly in this one, like electron withdrawing group, these are, right, electron withdrawing group chlorine, like that aldehyde C11OH is there and nitro is there, so the acidity increases. Means electron withdrawing group increases the acidity of your phenol. Similarly electron donating group decreases the acidity of your phenol molecules. Okay, I hope these things are very clear, acidity of phenols and acidity of your aromatic acids. Then basicity of amines. So as we know, the amines are basic in nature, right? All knows amines are basic in nature. So here, okay, in aromatic amine, so here we can see the order of basicity, right? So primary amine or the aliphatic amines are more basic in nature than ammonia and then aromatic amines, right? So this is also very important, you have to remember, right? So aliphatic amines are more basic, then ammonia, and then your aromatic amines, right? So here you can see, right, so aliphatic amine, so NH2 group directly attached to the sp3 carbon, right? And in aromatic amine, NH2 group directly attached to the sp2 carbon, right? So due to the aromatic ring, so means where the sp2 carbon is there, means that is the more electronegativity over there, right? Means in aromatic amine more electronegativity is there. Okay, so what is the effect of electron withdrawing groups and electron donating groups? So electron withdrawing groups, so basically these are the electronegative atoms, right? Means minus I effect there. So here is electron withdrawing group decreases the basicity, right? That is totally opposite to the acidity, right? Here electron withdrawing group decreases the basicity, while electron donating groups there is a plus I effect, right? Which inductive effect? That is the positive inductive effect, which increases the basicity over here, right? So in this figure you can see the aniline with electron donating groups and in aniline with electron withdrawing groups. Okay, so the electron donating groups increases the electron density of the benzene ring, making the aryl amine more basic than aniline. Okay, means here in this electron donating group you are seeing that the basicity is increasing, right? Means more basic. And in electron withdrawing groups that decreases the electron density of benzene ring, making the aryl amine less basic. Means that basicity is totally opposite to the acidity, right? So please clear your concept regarding your acidity and basicity concept, that all the name reactions that we have done, then whatever the like Lucas test, Hinsberg test, because these tests are the differentiating of your alcohols and the amines, and differentiating points of your SN1 and SN2 reactions. I hope we have covered all the important points from the organic chemistry from your point of view, exam point of view, right? So in the next lecture we will see the another subject or the another topic, right? So thank you so much guys.